So since we started, we've been working with like uints, floats, F64s, but in the space, like when you talk of cryptography, what you mostly hear them talk about is finite fields, right? Is this our first time of hearing finite fields?
Very last week.
Where did last week? Okay. So, like, just a brief explanation of what a finite field is. We have a field and we have a finite field, right? And when you have finite field, the finite there is there for a reason, right? Anytime we hear like finite, the next thing is infinite, right? So like the set of numbers are infinite. You can count up to a million, you can count up to a billion, like, and if you continue counting, it won't stop. You just keep adding one, right? But when we talk of finite field, we are talking about just a smaller subset of the normal set to work with, or a smaller subset of real numbers. And we can think of it as working mod a particular number, right? So there's a finite fields and there are the prime finite fields that's of prime order. Like when we talk of, those are like finite fields that comprise of numbers up to a certain prime. Does it make sense? So we won't be going into like set theory and all, but one thing we should just know is that when we talk of fields, there are like particular characteristics of fields. And let's say in a field, you should be able to add two numbers, right? When you add two numbers, it should also give you a number in that field. Does anybody know what we call that property? Closure. Good. So you add two numbers and you get another number in that field. So there's also the property of commutativity, right? Where, let's say if you add a plus b, it should also be equal to b plus a, right? Does it make sense? So we have closure, right? We have um, commutativity. So for commutativity, when you add two numbers, like a plus b, it should also be equal to b plus a. Then there is also the associativity property, right? When we talk of associativity, we're now talking about like three numbers, right? So, okay, let's say for closure, it means, say we have a, this is just like an example. This plus here can be any operation, either addition or subtraction, right? Should be equal to C, where C is also a member of the original set. What should I use for that? Let me use capital S, right? Does this make sense? Please, if it doesn't, ask questions. So for commutativity, it means A plus B should also be equal to b plus a. So if we swap the numbers, it shouldn't change the result.
Sorry, I think I got lost that. Or no, I didn't get where you said that the C with the S, the closure with the S.
Okay, let's say S is a set of all elements of the field. Right, so S contains all possible numbers that we are working with. Right, does it make sense now? So if you pick any two numbers from the set S and you add them, you should also get another number in that set. Okay, let's say like an example. If we have a set 1 to 5, right? Just a normal set 1 to 5. Can we say this set is closed? Under addition? No, right? Why?
Because 5 plus 4 is 6.
Yeah, because 1 plus 5 is 6, and 6 is not inside this set.
So is it possible to have a closed set like that?
Huh?
Is it possible to have a closed set like that?
Yeah, it's possible. It's possible. And why it's possible is when we start talking of like finite fields, mod a particular number. Okay, so we understand what closure is, right? This is just like a rundown. We're not going into like too much details. Just something that we can just use to at least continue with the implementation side of things. Does it make sense?
Yeah.
So commutativity, a plus b should also be equal to b plus a, right?
Yeah.
So like let's not consider this set again. You get? Let's just talk about, let's say, the set of real numbers now. You have maybe 5 plus 3. Is 5 plus 3 also equal to 3 plus 5?
Yes.
It is, right? 5 plus 3 is 8. 3 plus 5 is 8. So it's commutative. The set of real numbers is commutative. Does that make sense?
Yeah.
So let's also talk of like associativity. When we talk of associativity, we are kind of like talking about 3 numbers. Let's say we have A, B, and C. So it means that no matter how we order the addition or the operation, it won't affect the end result, right? So in this case, so if we do A plus B first before adding C, it should also be equal to us adding B plus C before adding A. Does that make sense? It's not clear. You know, when you see a bracket, it means that you need to perform that operation first, right? So in this case, what this means is that we need to add A and B, right? And then let's say we add A and B and we get D, right? Then we can go further to add C, right? While in this other case, we're adding B and C, right? Let's say we add B and D, B and C, we get E. Then we can now add A to it. So what they're trying to say is that whatsoever thing we get here after we've done this, and whatsoever thing we get here after we've done this should be equal to each other. So the order of the operation shouldn't matter. Does that make sense? So that's for associativity. Are we sure it makes sense?
Yeah.
But if it doesn't, ask question. So let's talk about like the distributive property. All this while we've been talking about one operation, right? We're talking about just one operation. And for our examples, we've been using addition, right? But when we talk about distributivity involves two operations. Does it make sense? So let's call our operation I also think of it as like addition and multiplication, right? So what distributivity is basically trying to tell us is that if we have something of this sort, let's say A, it should also be equal to, right? Does this make sense?
Yeah.
So we're just distributing this multiplication operation over this part in the parentheses. Does it make sense?
I'm sorry, is this supposed to be A times B plus A plus AC or A times B plus A times C? Like the plus C, like I was thinking it was going to be
No,
A
this.
times C.
Is it this?
Yes.
This
Okay,
times.
times, okay.
Yeah, this time. So does this make sense? So we're not going into the details of like set theory and all, but like there are different groups of should I say, let's call them groups. So groups would be the right word. Like we have fields, we have groups, we have monoids, we have like there are semi-groups, there are a lot of them, right? But why we work mostly with fields is because like fields have all these characteristics. When we hear of groups. Groups have just one operation, right? They don't have two operations. So since they don't have two operations, distributivity must not hold for groups. Does it make sense? Since they don't have two operations, distributivity, when you talk of distributivity, you're talking about two operations. But groups have just one operation. Right. And when you hear about group, you're just talking about one operation. When you hear about an elliptic curve group, it has just one operation, addition. You can't do multiplication in an elliptic curve group unless you want to talk of bilinear pairing. We're going to still talk about all this when say we start getting into like polynomial commitments and all. Right? But fields in the other case has two operations. You can do addition and you can do multiplication. Right? There are still other properties like inverse. Right? Huh? Yeah. Yeah, for both operations. So, for a field, it needs to have both an inverse for both operations, right? So, let's say for addition, for the addition operation, it should have an additive inverse. Like every element in the group should have an additive inverse. So just think, should I talk about the identity before I talk about inverse now? Or let's just continue. So what is an inverse, basically? Like, we can think of an inverse. For the additive inverse, we can think of it as another number that if we add to that number, we are going to get the additive identity. Okay, so first of all, let's talk about the identity element first. So the identity element, sorry, is everybody following?
Yes.
Please, if you're not, just ask questions. Like, you may need to go over it again. That's by the way, but like we are here in class, and if you have any questions, just ask. So when we talk about the identity, we're talking about any element of that field that if we multiply it with another element, we are going to get back that element. There's plenty of elements in that statement, right? Okay, so let's say we have A, which is a member of the field, right? If we multiply it with E, let's call E the identity. So every operation is going to have like an identity. Like we are going to have like an additive identity and also like a multiplicative identity. Right? So let's say if we are talking like with respect to the additive identity, we say we have an element A, and if we add it to E, where E is the additive identity, right? We are going to get back A. Does this make sense?
Yeah. E will always be zero.
Huh?
E will always be zero.
It depends, right? But in this case, we are talking of additive identity. So
Yeah.
the additive identity of the set of real numbers is zero, right? Or the set of integers. So in this case, we can think of like if we have, for example, 5 plus 0, we get back 5, right? If we have 1000 plus 0, we get back 1000. So here we can think of 0 as the additive identity. Make sense? Now let's talk about like the
Will you always be zero?
yeah, in this case.
Yeah.
Different fields may have like their different identity elements. So different fields may have their different identity elements. But when we're talking about like the set of integers or the set of real numbers, like 0 is the identity. Is the additive identity. So for the multiplicative identity, we have A times E should also be equal to A. Right? Where E is the multiplicative where E is the multiplicative identity. So when we're talking about like the set of integers, which number is the multiplicative identity? 1, right? Because 5 times 1 is 5, right? And 1000 times 1 is 1000. Everything makes sense up to this point. So now let's talk about the inverse. So when we talk about the inverse, what we are trying to say is that every element in the group, or every element in the field should have an inverse, right? And the inverse is basically like any number that when we talk of the additive inverse, we are talking of any number that when we add it to a certain number, we are going to get the identity element. Does that make sense? So let's say A. What can we use to? Okay. Like if we're talking about like the additive identity, right? Say A plus. Okay. We should get the identity element. Does this make sense? So if we're looking for the inverse of 5, for the additive inverse of 5 over the set of integers, what is that going to be? Negative 5, right? Because 5 plus minus 5 is 5 minus 5, right? Which is 0. And 0 is the additive identity. Does it make sense? Yeah. And how about like the multiplicative identity? Yeah. So it's the multiplicative inverse is any number we multiply with a number to get the um, multiplicative identity. Does that make sense? So let's say for 5. Okay, so let's say A where E in this case is the additive identity and E in this case is the multiplicative identity. So in this case, for example, if we're talking about like 5, right? 5 times what will give us the multiplicative identity? 1 over 5. 1 over 5 is still 5 to the power of minus 1, right? Will give us 1, which is the multiplicative identity. So, like, does everything, does all these things make sense? Small again. So basically you won't need to be thinking so much about this, right? Because let's say if you're working with a finite field that have been implemented already, all these things would have been implemented. So you just have those should I say functions, you can just call them as like black boxes, right? If you want to get the additive inverse of a group or of a field, you can just, like, based on the implementation, you can just call a function and you get back a result. So unless maybe you now want to go into like implementing a finite field, like on your own, you want to implement a finite field, then you need to now start like factoring all these things, like going in depth into them. But like mostly we're going to be working with, you're not going to be implementing your own field for this course. You can go back and implement it, let's say on your own. But in this program, we're going to be working with Aquox. Aquox is a library that has like different, a library in Rust that has different field implementation, not just field, like they have a lot of cryptographic protocols that they've already implemented that people can use to build things, right? Yeah, Aquox. So there are also other libraries, like there's LambdaWorks. I think there are a whole lot of them, right? But like Aquox and LambdaWorks are kind of like mostly Aquox. Like most protocols, like just use their implementation, since like they have efficient implementation of some of these fields. On your own, you can go ahead to create your own library and probably make it way more efficient than Aquox. People will use it, right? But the thing is, like, the experiences of all the people that came together to build Aquox is one of the things that has made it stand out in the industry, right? So we're going to be working with Aquox, and for univariate polynomials that we've implemented already, we are going to need to change the I said the type, right, that we've been working with, so a field element, because from here onward we're kind of like going to be working with field elements. So like I said, no need to go and implement your field. We're just going to use the Aquox library. So before we continue, does anybody have any question? So far, that was just like a brief high-level rundown of fields and all.
Alright, my question is, since we are talking about field, and we know that the field has two operations, we only consider the two operations because the two operations are supposed to be working concurrently. Is it here, you only mention it when we talk about distributive property? While we are considering addition, do we need to, for example, when we implement it, do we augment it or reduce two of them together? But for example, when we talk about closure, it's closed under addition and exclusion. Do we put them together or we only consider, let's say, closure under addition, like we are done? Do we separate them or we put them together?
Oh, once we're talking about fields, right? For us to be talking about a field, that means it's closed under the both of them. Yeah. So we don't even need to think about that again. Like, in as much as we're talking about a field, for it to be called a field, it has to obey all those, like have all those properties.
To verify whether it's a field. We need to verify whether it's a field.
No, you don't need to do that because the people like Aquox, they've implemented it already. So it's their duty to do all the verification. So when you want to use it, you're just using it as a field. I don't know if it makes sense. So there's also, like, I didn't really go in depth into it, but like finite fields. I mentioned finite fields, right? So when we talk of finite fields, we are talking about like a subset, yeah, of the fields that is finite, right? But for us to call it a finite field, that means it has all the properties of a field, even if it is finite, even if it is small. It still has all the properties of a field, like all the properties we are outlined. If we add two numbers in the field, we are still going to get another number in the field. If we multiply two numbers in the field, we are still going to get another number in the field, right? It's also distributive, and it's also associative and commutative, and has an identity, has inverse, like all elements in the field has an inverse. That's kind of like just the summary. Or we can just, let's just do like a small example, right? Let's say we want to work with a finite field. What should we? Mod 7. Okay. Sorry. So we're working mod 7. Mod 7, right? That means the maximum number in the field will be 6. Whenever we get to 7, we roll back to 0. Right? And the order of this group is the number of elements in the group. So in this case, how many elements are in the set? There are 7, right? So the order is 7. So let's try to add 2 numbers. Now, I remember when we are talking about commutativity, if we add 2 numbers, it should also give us, when we're talking about closure, when we add 2 numbers in this set, we should also get a number that is also in the set, right? So let's add, which number should we add? 5 and 6, right? So 5 plus 6 is 11, right? But we're working mod 7. Mod 7. And what does mod 7 mean? Yeah, we divide by 7 and take the remainder, right? So 11 mod 7 is 4. Why? So we have 6, right? 7 brings us back to 0. 8, this can be used to represent 8 too. 9, 10, 11. Right. So if we talk of like 20, we just go 6, 12, right? 18. Yeah, wait. 6, 12.
7.
7.
Yeah, every 7 is 0.
Yeah. So we go to 6, right? 7, 8, 9, 10, 11, 12, 13. Right? So if we see 13, we're still talking about 6, right?
Yes.
So 13 mod 7 is equal to 6, right? So we'll get back like 14, 15, 16, 17, 18, 19, 20, right? So basically it's just like we divide and take the remainder. You get? And why we work with finite fields in cryptography, or like one of the reasons we work with finite fields in cryptography is because we can see 6 can be represented, 13 can represent 6, right? 20 can represent 6. There are a whole lot of numbers, infinite amount of numbers that can also represent 6, right? So when we're talking about 6, you don't know which of these numbers we're actually talking about. I don't know if that makes sense. So it can be one of all the numbers that represent 6 that we may be talking about, but you won't actually know the particular one unless you try like every single one of them. So this is just like, this example is just one basic example, right? Well, we can also do like multiplication and like work mod 7 and all. I don't know if anybody has any question with respect to this.
Yeah, I have one. It does good, but how does one sell come to the
Huh?
like that's the field, right?
Yeah. Yeah.
But how do you define what sell as part of the field? Is it the operation of the
No, 7 as itself as a number is not part of the field,
yeah,
right?
okay.
So we are saying we are working mod 7 that means the biggest number in the field should be like 7 minus 1, which is 6,
Okay, so
because we're actually starting with 0.
okay, so the field is defined by the largest number should not be higher than 7.
Yes. Yeah. Okay. So is everybody with us up to? Okay.
Are all the elements of a finite field consecutive?
No.
So it can be 0, 1, 2, 5, 6.
Yeah, it can be jumbled up.
How do you care about
They are not always sequential.
So how would you do a modulus operation on project?
A modulus operation.
Yeah, like this same operation, but with a finite field of 0, 1, 3.
The thing is, like, every field will have a generator, right? So a generator is a number that you can use to get subsequent numbers in the field, right? Or in the group. So,
Excuse me. You mentioned generator now.
yeah.
Does that make it cyclic?
You can, right. The generator is a number you can use to generate all the numbers of the group.
No.
It must not be cyclic.
Not cyclic.
It must not be cyclic.
Like this, which generator do you using now?
No,
I
you
think that
mentioned
was
in-
5. What's that? The one that you kept adding.
Okay. No, but that's not like that's like cyclic groups. Cyclic groups are groups that, like, when you get to the end, it circles back to the beginning,
Yes.
right? But
Something is the same.
Huh?
Something is like the same.
yeah, but like you can think of them. I won't say they are.
So I think what you said here now, like for instance, in 7, 2. So right, let's say we have number 2. It can also be 9, right? It can also be 16. Like we keep adding 7 to it to keep changing. So I think that's what you're referring to, right?
Like to generate the elements in the field, or
Yeah, I thought that was what you're referring to as the generator.
okay, for this one.
Yeah.
Okay, no, I was just talking about
General field in general.
fields in general.
About the fields now.
Wait. Okay.
So, are we the one determining our finite field?
You don't need to, like, they've been implemented, but you can pick one you want to work with. Like Aquox has a lot of different field implementations, right? So you can pick the one you want to work with. So you can work with, let's say, the BN254 field. They also have the BLS 12381 and like some other fields that they've implemented already. So all you just need to do is, like, which field do I want to work with? You can just pick it and work with it. Or let's say you now want to work with something different. Right? They also have a way you can instantiate a field of your own choosing. But in that case, you need to, like, provide the mod that you're working over and also the generator of the field.
So if I have higher lengths
Huh?
in the fields now, if I have, like, let's say we are doing 0 to 6 here, I decide to go with back 0 to 4.
Yeah, you can
What's
decide.
the use of that smaller field compared to this big one?
The smaller field means it's going to have smaller number of elements, right? And smaller fields are technically not secure because you can count every element in the field easily. So why we kind of work with bigger fields is because it's difficult to count all the elements, or it's going to take a longer time, right? So that's why you see them working with, like, fields up to 256 bits. because those fields are like very large and it's not easy to enumerate or like count every element in the field. So basically for security reasons, that's why like they work with bigger fields.
Is the mod 7 the reason why this field is finite?
Yes. Once you have a field mod something, it's a finite field.
Okay. Does this particular field have a generator?
For this field,
And
if we take 0 out, then we can think one can be a generator, right? Because if we keep adding 1, we can generate all the elements in the field. Right.
Sorry, I'm just, it's not, I don't think it's all the numbers mod. Let's say for instance, mod 4, it's not a finite field.
Okay.
Yeah, so it's all the prime numbers. So for instance now, mod 2, mod 3, mod 5, mod 7, mod 11, all those prime numbers, all of them are finite fields, but not all the
Yeah.
integers, for instance, are finite fields.
Yeah, that's true.
Yeah, all the
So
prime numbers.
they are-
So are those not
Yeah,
prime
that's
numbers?
true. Like,
Yeah.
sorry, there are prime numbers or prime fields are, yeah, because of the prime, they now satisfy, the prime makes them satisfy the whole properties of a field, right? So it's not just all numbers mod a certain, they say that it's like a field, right? So there are some that are a field, there are some that are not a field. But why we have prime fields is because like most primes, like the fields that they generate actually satisfy the properties of a group. Thank you. Yeah.
So for us to create the finite field, we have to make use of a prime number as a module.
Yeah. But the thing is, there are different ways to go about that. You don't want to be the one like creating, because you need to like verify all these things. You don't want to create a finite field that does not satisfy, because it may look like it's satisfying, but a point it may not satisfy maybe for a number in the field, right? So there are ways they use to verify all those things.
So you mentioned that like a smaller field is generally like less secure than the larger one. But you also mentioned that like the reason why fields are used like in cryptography is you don't know essentially what one number like represents. But if you have a smaller field, like numbers represent more numbers, if you get what I mean. Like if in this example you have like 0 to 6 mod 7, and you said 6 could represent like 13, 20, moving forward, like
Sorry, the security of the field is not based off that. Sorry. Yeah. So basically any number can be represented in, what I was trying to get at there is that any number whatsoever can be represented in a finite field. Yeah. So it's going to fall, it's just like if you're working with what do they call it? Is it a hash bucket or like you have a set of numbers that things that, or set of buckets, right? That something can belong to. So if you hash it per se, it can only fall within one of those buckets,
yeah,
right?
I get the thing.
Yeah. So any number whatsoever can be represented in a finite field.
I'm trying to understand why exactly only prime numbers, mode of prime numbers are finite fields, while the other numbers are not.
I don't know why.
Let me tell you.
But okay.
For example, when we consider mode 4, for
Yeah,
example,
yeah,
prime numbers. When we consider mode 4, for example, prime number, what are the elements in mode 4? 0, 1, and 2, there. So if you get if you are trying to do any operation, for example, if you pick two elements and put the two operations there, those two elements can give you two different elements in the distance. Because when I do this times this or this, it should give me a unique element in the two. But it is not fine if it's a distance. For example, I have to construct an example.
So you are using
I can,
with solver.
yeah, if I'm
So
using
that's
the
0
for,
to 3.
yes.
So let's do
For
one
example
plus
now,
2. For 2
don't
times
let,
3.
don't let's use move 4. Move 4 is smaller. Let's use move, let's say move 8.
Okay.
Move 8 for example. If I do 4 times 6, I have to calm down and construct an example, but in the nutshell, in summary, what I'm trying to say is that two elements, when you put an operation, should give you a unique element in the distance. But if it's not, if it's divisible by itself, it can give you two.
As if any element in that system
It's divisible by each
they are
other.
not relatively prime.
They are not relatively prime, and the DCD is not one.
So like any number in the, let's say in 4 now, 2 can divide 4.
Yeah.
So I don't know, it breaks one kind
Yeah,
of
you
relation.
can't you can't find the multiplicative inverse there.
Yeah. So but if you see in let's say 7 now, no n number in that field
That will, the DCD is
can
always
divide
one.
7. So
Yeah, but when it's 7, it becomes 0.
Yes.
But if it is 4, it can become 2.
It can become
Yeah.
2, it can
yeah,
become
yeah. So
0.
it doesn't have
Because of
the
that,
multiplicative inverse.
most really in that is not satisfied. So that is why it's not fine. It's not a full. Right.
Hope that answers your question. Right. Okay. Okay, so let's okay, so let's look at. Sorry, does anybody have any other question like with respect to this before we, like with respect to the whole field stuff? Does anybody have any other question with respect to it before we look into like AppWorks and how we can use it in our code?
Can I go over what's the generator again?
Okay. The generator of a group is a number that can generate all the elements in that group.
Including 0. Apart from
Most of the time,
Yes,
they don't
sir.
give you the generator, like
Yeah.
it's fixed. So they can't give, if 0 will work, if 0 will make you generate other elements in the group, if 0 can be the generator. But if it's not, they will give you another element that will make sure that it's give you other elements when they put the operation inside that group. So in mode
Almost.
6 or mode this now, 0 is not a generator because 0 cannot be a generator because if you add 0 to any number, it's give you that same number and you have not gotten other elements in that group. So that is
Like also like 0 to the power of anything is
zero.
still 0, right? So most times like they usually remove 0 from the sets. Like when they're talking about generators, they usually remove 0 from it. Any other question? Any other question? Okay, so we're going to be looking at these are univariate polynomial implementation, right? So we'll just look at how to like add a finite field or how to add like AppWorks so that we can use. Is this okay? Maybe it's not so much. So first of all, we need to like add the Aquox library, right? So that's cargo. So cargo add ff, cargo add arc underscore ff. So it's like arc underscore finite field, right? So once you do that, then it adds the arcff library for it, right? No. No, this that was what I ran. This cargo add, yeah. So once you run it, it adds arcff to your dependency. So we're going to be working with prime fields, right? So we now need to import like the prime field traits from Aquox, right? So we'll use arcff, that's the prime field traits. So there are a lot of functions on this prime field traits that we'll be using in the course of like our implementation. So basically there's no need to go about like implementing your own prime field. This is what we are going to be working with. So how many of us are conversant with like generics with respect to Rust? Okay. So when we use F64 here, F64 is a particular type, right? It's a particular type and it restricts the type we can use for our coefficients to an F64. But now we want our coefficients to actually be elements of a prime field. And one way we can go about that is like we can use generics. Instead of x64, we are going to make it f, right? But now what is this f? So it's complaining, it doesn't know what f is. So we need to define what f is, right? I want f to be anything that implements the prime field trait. Does that make sense? So we want f to be anything that implements the prime field trait. It makes sense, right? So if we can see here, it's complaining. So we are missing the generic for the struct type. We have defined the univariate polynomial struct here, and it has a generic f, which we said that f must implement the prime field trait, right? So now in this implementation block for the univariate, we need to define, we need to also take f here. But this implementation block does not still know, like there's a restriction, right, to what f should be. F must implement the prime field trait. So when we put this f here, it doesn't still know what f is, right? So we need to define it, f, and it should be anything that implements the prime field trait. Does that make sense? Makes sense, right? So here we can see a coefficient, it's actually still at F64. So we need to change it from here to be the generic F.
Do you know why we have to put the F in front of the increments?
Is to define what the F is. Here, if we don't put this, it doesn't still know what F is. We're just telling it use F as a generic, right? But we need to define what F is. If we put just F here, there was a restriction here, right? This is kind of like a restriction. We're saying F should implement this trait. So if we come here and we don't put that restriction too, then it will be a problem, right? Because us not putting that restriction means that F can be anything. So we also need to put that restriction here that should implement the prime field trait. I don't know if it makes sense.
Yeah.
Okay, so let's go. Where next is it complaining? Here. Expected F64. Okay, they evaluate. Yeah, so it takes F64 and returns F64. So we're going to make it F, right? I also return F. Why it's able to see F on this scope is because we had already defined F on this implementation block. If we defined F on the function, like on the function itself, because you can also do something like this, right? Where you define F. Say we have a function, a normal function outside the implementation block. You can also do something like this, like if we want that function to take a generic. But that's not necessary since we had already defined F here.
Sorry, please can you come again?
Like this F we defined here is available for all functions within this implementation block. That's just what I'm trying to drive at.
So if we're not like inside the implementation block, how do we have done it just for a function, a particular function?
Just for a particular function,
Yeah.
that would have been, let's say, function hello, right? Let's say it takes name. My name will be a string, right? And it returns, let's say, string too. But if we want this name to be a generic, let's use C, right? I just return so it doesn't complain. Or let's say I can't find T in this scope, so we need to define what T is, right? Say C is a generic. I don't know if it makes sense.
Yeah.
So if we want to put like restrictions, for now, like T is just like a generic. We have not put any restriction to things that T must implement.
Okay.
So if we want to put restrictions, we can go ahead to put like restrictions.
Okay, so that F is like a generic in that,
Yeah, in that place.
and then prime field.
Prime field is like a restriction that anything F is, it must implement
Prime
the prime field traits.
any other letter.
Yeah, you could have used any other letter instead of F, right? Yeah, you could have used any other letter. Does that make sense?
Yeah.
Okay.
So that means we are changing everything. Anywhere we see that F.
F64, yeah. We need to change it to F. Yes.
But the prime field trait is already defined already.
Yeah, the arc FF. That was where we brought the traits in from. So anywhere we see
So the implication of this is that does that help represent like
does
represent like the field?
yeah, it
field that we're
represents
working with
yeah.
now?
For now we have not yeah. So when you want to test, you now need to pick okay. F needs to implement the prime field, right? So which prime field now?
Now, okay.
That's
What if you wanted to print somewhere?
somewhere here.
Yeah, like wanted like the next one of me.
So a particular prime field.
You want to print something.
Okay, you want to print something.
Yeah. Instead of like testing, you want to like print. How do you put your prime, like the field, what field it is?
Mm,
Because
I don't know
we
if
still not
I-
specified it anyway.
yeah, we've still not
So let's say
specified
I'll just like,
it.
oh, call this function and then print this one instead. At
The,
some
the
point,
prime field, I think like the prime field traits should also have like debug.
defaults.
Right, yeah. Like debug is you know yeah, the debug traits. So you can use the debug traits to like print or to string. Right. I don't know if it makes sense. So
Sir.
I'm not how
I wanted to add, so, you know, in most of our operations, we made use of some mathematical operations like times and plus. So now that we're using the prime field, do we still have to use that, or the prime field trait has its own implementation of those mathematical stuff?
yeah it does. The prime field trait has.
Okay.
So instead of us to use F times something, the F dot function.
No, like you know what's when we're implementing this more so the prime field already has like implement more for prime field.
Okay.
You get
What about those of us that implemented without this structure? Like we use multiplication, like when we're working on the evaluate.
you don't need to think about like it handles it. You don't need to think about that again. Like still your normal multiplication.
Yeah,
It will work.
it will work. Okay.
Yeah.
Building on his question, like you know, when we're implementing this more now, for instance, he said we are just implementing it because the Rust does not understand polynomial, so we are trying to tell it how we want it to carry out the multiplication when it sees a polynomial. So now, does the prime field trait now as multiplication for polynomial, or are we still using this kind of our implementation for
No,
for it?
you need to define your own multiplication for polynomials because you were the one that created the polynomial struct, right? So you still need to do that. But within the polynomial, where you're actually doing multiplication between numbers, you don't need to, like that one is taken care of.
Like
I don't know if you.
you see line 113, right?
Yes.
You can see solve the quotient I times RHS the quotient
Yes.
I. So before you're using F64 inside all those things,
Yes.
right? So Ross knows that okay, if it sees multiplication, it knows how to multiply 2 U side of 2 F64. Now you have replaced it with field.
Yes.
You don't need to change your code.
Okay.
Because of Aquox has already implemented more,
Okay. It's the same thing as
Yes. So when it says the multiplication, you check.
Okay.
Realize that, oh, this is a field, this is a field. And
Yes.
it's gonna check the library. Does this library have more for field? And then you say yes. And it executes the more for field. So you don't need to change anything.
So basically the code.
Yeah.
So, I have a thing like that. We are implementing this as of like, so all we are just doing is just changing the number.
Yeah.
Yes, just the data type.
Yeah.
Yeah. Yes.
I want to see my power. So I change to the field.
Okay, so okay, the scalar, yeah. I need to the structure, I think. Yeah. So we can see like that situation here, right? So first of all, it was like a reference to a field element times a reference to a field element. Arcbox didn't implement like multiplication of those references, so we now had to dereference. And after we dereferenced, the multiplication, like Arcbox have already implemented the multiplication, so it doesn't complain again. Does it make sense?
Yeah.
Okay. So that's the basis function. Let's say the basis function.
Is there like this greater than
You say
because greater than
greater than or equal to,
Yes.
less than or equal to. I think. I think yeah. Check if you're actually if you're actually doing it on a reference or on a value.
So greater than is the power of implementation. I don't know if there should be some point. That'll be minus 1 times.
Okay, the negation. Oh yeah. So so it has the dot neg function to convert it to a negative. Huh? Yeah, the 1.0 we need to convert it to to a field. So they have this 0. Sorry, 1. Yeah. F1. Yeah. Let's finish off this guy. What's this? Yeah, okay, the sum function, right? No. Yeah, for sum and product. But let's fill out this.
You have to do the same thing.
Huh? Yeah, we need to define it.
The same thing for some like
Conada sign floats. Yeah. No problem. Yeah. But everybody understands what is going on, right?
Sorry, sir.
Yep.
Yeah. So I was understanding it until when you started implementing it inside the. For instance, when you use that, when you were instantiating the numerator, when you were creating the numerator variable.
Yeah.
So my question is, I thought the implementation at Go covers all of it. Why are you implementing when you are doing the numerator variable itself?
The numerator variable.
Yes, like at that point when you called, the
You know-
numerator is an instance of the variable.
Yeah. See, initially what was here was minus
No,
x.
not this one itself yet. That's
Okay.
F at the top. No.
Which one?
That's 91.
Okay, 91.
Yeah, that F. You have put it in front. Like
Yeah, we're saying that the numerator should be, we're defining the type, right? And the univariate polynomial has a generic, right? So we need to define the type of the numerator, which is a
I thought it
univariate
was in the structure
polynomial.
already, like that everywhere there, the invariant is to be used, like it has a type of field or something like that.
So I think you could have used some. That what you mean?
No, like when it was F64, there was nothing there at all.
Yeah, because it's new, right? Here. They do.
No. Are you talking about without the F?
Yeah, without the F.
Oh. And but if you look at the previous definition of struct, it was just struct in a very open bracket.
Oh, so
But now we added this.
So now it is now struct, the event poly then F. Oh, so that means everywhere we are. Oh.
So anywhere we see univariate poly, we need to put that angle bracket F. Does it make sense? And we're working with fields. Anywhere we see a number, I hear it was 1, so we use F1. Right.
It's predefined. 1 and 0 is predefined.
Yeah, 1 and 0.
Yeah, for all the prime fields.
And since the addition and the subtraction is like word, not signs. Like instead of putting a sign, you have to say any.
Okay, for negation. Yeah, that's just they have the method, but could have also done minus F. Yeah. I think parents were having an issue with the referencing thing. So this is a test now. You can't just use F, right?
So yeah. So in the test now we need to like
Give a
concrete value.
for the field.
Yeah.
Oh, it's not fully taken.
So there are a lot of ACOC actually has a lot of implementations. Okay, let's just like a lot of field implementations. So we can decide to use maybe the ARC BN254 field, or we can decide to use the ARC BLS 12381 field. There are still other like field implementations, but the common one is mostly these two, right? So we need to add it.
Yeah, 245.
Sorry, 254.
Yeah, they list online. All the ones that they are doing.
Yeah. So once we add it, we're going to see it has been added here. So we now need to import that. I will need to implement FQ. So FQ is kind of like an implementation of the prime field. Or the BN254 is like the implementation of the prime field. So once we've imported FQ here, we can use FQ here.
The Q, is there something for?
You know, like that was how they exposed it in their implementation.
It's related to
Like that's the
Yeah.
function we can access, or
Yeah, we can access it.
FR.
For what?
Yeah, there's also FR.
How are we going to know the one to use?
See, there are,
They're different from So now just choose one.
so you can see there's FQ, there's F12, there's F2, there's F6. Right.
Questions here. What are we looking for? What are we trying to do? And
Okay.
or should we just go to the docs and look at it?
Okay. What do we need it for? Right. You know, initially in our program, we just stated that F should implement the prime field trait, but we did not like anybody can just implement the prime field. Like anybody can implement something that implements the prime field trait and will be able to use it, right? So when it now comes to tests, we need to pick a particular implementation that we want to use for the test, because now we are working with concrete values, right? If you want in your test, you want to be able to do something like 3 times 5 should be equal to 15, right? So now we want to work with like concrete values, right? That's why we had to now add ArcBN254 to our dependencies, because ArcBN254 is the like the 254 bits field, right? The ARCOC has already implemented. So FQ is kind of like, you can think of it as like a field element in the BN254 field. ARCOX, they already exposed it for us, so we just need to pick to use it. We're not going to be talking about things like field extensions for now, but if you check, you'll be seeing like things like FQ2, FQ6. Those are kind of like field extensions, but we're not talking about like field extensions for now. So it's maybe when we start getting into when we start getting into the polynomial commitment scheme, where we start working with groups. That's why we now need to work with like field extensions, but there we'll be using like parent friendly codes, which BN254 is not, it's not a parent friendly code, I think. Forgotten. But then like do we understand the reason for the FQ now? Because we need concrete values to work with. So initially in the code it was F, right? We need a generic F that implements the prime field trait. So now we are saying univariate polynomial and want to use FQ, meaning that FQ actually implements the prime field trait. These are tests, and we brought in FQ from the BN254 library.
Why we bringing this in?
FQ, you can think of it as like a field element in the BN254 field. Like the definition, you can think of it as like the definition of a field element in the BN254.
Which is the prime field?
Yeah, which is a prime field. So when we're defining our code, we were using univariate polynomial F, right? Where F should implement the prime field trait. So now we are using like a concrete implementation, FQ, meaning here that FQ actually implements the prime field trait. If FQ does not implement the prime field trait, we will not be able to use it. Like if we defined something like let's say struct FQ and then it's going to complain. So the trait FQ prime field is not satisfied. Does that make sense? Makes sense, right? So we actually need something that implements the prime field trait. That's why we use the BN254. So now everywhere we have a number, we need to now, yes, it has to be a prime number in the field, right? So FQ has the function it exposes, FQ from. So we can just put 1, right? FQ from 2, FQ from 3.
So just a question. You have like an infinite number of fields.
Yeah,
So now which particular field is this particular field?
It's working with the BN254 field. Yes.
Okay. So you carry it like, let's go back to math and say, how can we relate it to mathematics? Like
So
the BN254.
So it's the BN254 field is a field where the prime of the field is like 254 bits. Yeah. So that's like, because this is the definition actually. This is, so you can see it here. This library implements the BN254 curve that was sampled as a part of blah blah blah. The name denotes Barreto. Now I don't want to spoil somebody's name. Curve of embedding degree 12 defined over 254 bits prime field. You get. So like Aquox has implemented the field already and we're just using it. So this is the base field, which is Q, which is this large number here. And this is the scalar field, which is R, which is this last number here. This large number. And it's like the equation of the curve, like the G1 and G2. So these are just like more information about the field. Yeah. Well, the main thing is that like the field has been implemented for us already, and we're just using it for our purpose. So that makes sense.
Yeah, so two quick questions. When we say a prime field, now, though it is prime, like let's say 7, so we are just saying the modulus, it is in modulus that prime number, right? Meaning that the numbers contained in it is still 0 or 1 to that, to the 1 less of that number, or is it like when we say a prime field, the number in the set, all of them are actually prime numbers, or they are still 1, 2, 3, 4 to that 1 less of that number? That's one. Then 2, when you used FQ from 1 now, since you said, is it interchangeable with 1 that you said they implemented? Meaning that when we use 1, we can actually use FQ for 1, and when we are using FQ for 1, we can actually use 1. Like, or
Okay. So this, in the code, we didn't know the field we are talking about. We just want something that implements prime field. So we don't know the particular prime field. But we know that any prime field it is going to have an identity element, right? 1. So that F dot dot 1, what it just does is it figures out the prime field that we are using to run the test, and it gets the identity, the multiplicative identity element of that field. If we use a different field, let's say the BLS 12381, we are not going to go and change our code again. Like that F1 is still an F1, like it's a function that is already exposed. When we call that F1 function, we just get the multiplicative identity element of whatsoever field we are using in our test. I don't know if it makes sense.
So that means it is interchangeable with this FQ from 1 also.
Yeah, it's if you write a function to check the equality, it's the same thing.
Then about the set of a prime field, like
Okay.
is the set like just a set of prime numbers, or like
No.
they are still consecutive numbers?
No, not all elements. It's not a must that all elements in the set or in the field will be prime numbers, right? It's not a must. So you can think of it that way, as a set of consecutive numbers up to,
That number,
but not including the prime, right? You can think of it that way. Although like it's not always consecutive, it's not always sequential. That's what we're trying to go at.
They
When
contain all the numbers.
it contains all the numbers in that set that satisfy all the properties that were outlined that made it a field. For us to even call it a field, that means every element in the set must, or the whole set must satisfy the properties of a field. Right? I don't know if it makes sense, or if I answered your question.
So, are we saying that? Let me use that 7 for instance. Are we saying that I understand that this this FQ now is implementing a very big number and stuff like that. So I understand how massive it is. So are we now saying that in that set, like they are, if we now start counting from like 1 to that big number. There's a possibility that there are some numbers that do not satisfy the field that does not satisfy that field and is not included
It's
in
not
that
there.
set.
It's
Is
possible.
Is that possible?
It's possible. It's possible. Yes, it's
But that's
possible.
not prime field.
Well, that's not prime field. Like, that
Yeah,
won't be prime.
like that can be like a multiplicative group or something like that, right? Where if you want to count all the elements in the group, you like have a generator and
Now,
you
now I was talking about prime field now, like
okay,
for-
prime field.
Yeah, for prime field now, like going back to my original question, like my question was, does it mean that mode 7, for example, 7 is a prime number, has all the numbers between 1 and 6, or say mode 23 has all numbers between 1 and 23, or is it like for some reason some of the numbers inside that set does not satisfy the field, so it might not be in that set?
I think if we're working with prime, like that's the essence of the prime field, right? If we're working with the prime, then all the numbers will satisfy.
Will be inside. That is
Yeah,
1
since
to
we're working with prime.
0 to 0
0 to n minus 1 or p minus 1.
So if you give yourself any set, think of any set you like. So for you to be sure that that set you are giving, for you to call it a field, it must satisfy 6 property: closure, commutative, associative, distributive, must have identity element and inverse element. So you will not check all the elements in that field. Do they satisfy that? So if they satisfy, irrespective of their order, maybe it's 1 to jump from 1 to 20 or 2 to 30 or whatever, you are not concerned with that. So if it satisfies those conditions, then your next move will now be that, is this a finite field? So when you define the set, so that means is it countable? Is it countable? Permit me to use that, but that means can you count it? So if you can count it and it satisfies that is a finite field.
No,
So this question is prime field.
For prime field now.
Prime field is not satisfied.
No, I think that's because like what I was asking is like are there some numbers that we have to skip that we can't use for prime?
You are the one that we know. You are the one that we know the numbers. So if the number
I think
does
you-
not have to, every element there must satisfy the 6 conditions.
I'm
If you
speaking
put the
about prime
redundant,
field.
if
The
you
prime field
And
not
this question is
satisfied.
prime.
And that's what I'm saying.
You get it now.
Yeah, I guess.
So it's like, I think there'll be a problem that if anything more, a field more, a prime satisfies all of it. So then you don't need to care again, you just pick any prime number. And
Yeah, that's why we were saying earlier that like if it's 7 now, 7 is prime, so no element in that field is like can divide 7. So it is relatively prime with 7, so that's why it's prime field.
Even if we have 2, 4,
No matter what can divide 7 is just
1 and 1.
exactly.
But what's the name of that package again? The DNS.
BN underscore BN 254. What was there before?
Why do you need to define
Okay.
each from like so what does it return? Does it return 0 to 5?
Hmm?
This FQ from 5, 0 and 2.
Yeah, it returns like this FQ from 5. You know, 5 is a U64 or whatever. So we're trying to put it in the field now. That is what this FQ from does. So it returns a field element. A field, like, it takes 5 into the field. So we can now treat 5 as like a field element.
So it's just like working like string from.
Yeah, string from something.
So the prime field, whatever number you pass, is going to more the prime.
Mod it.
So yes.
Okay. So we've attended to everything. So if we should run our test, it should just work. Right? Because we didn't do anything different. Right? What if it breaks? Yeah. So our 5 tests pass. We've been able to convert like numbers to field elements.
Please, can you show where you imported the BN 254?
Okay.
Hold on, test.
Okay, yes.
So you can just scroll up a bit. No, it's the test side.
Okay.
Then this side, that's the
Thanks. Are you okay?
Jerry, can you turn off this?
Okay. Does anybody have any questions so far? Like,
Yes.
D.
Why we use discrete? But the ones that define is very
Yeah, but the ones that define the very.
So going forward, all our implementation will be using the prime field.
Prime field.
Because I know that when we were trying to do that Shamir sharing circuit, one of the issues that we were having was precision error because of the fact that we are using float numbers. So even though we have like at the end the coefficient is like let's say 3.1245.
By the time you round down,
if we round down, we will not be getting that the two values are not correct.
So what we're going to do is like For the Shamar implementation, you're going to change it to use a field, right? And hope that works. So we're working with fields now. Like anything we implement, we'll be using prime fields.
So does that mean you can still convert for the Shamir number because I use provided from 64 so that's when so now convert it to field.
Like anyway, everything we're going to be doing now, we'll be doing with prime fields.
So the thing with prime fields that we cannot specifically see that this is the actual answer. I don't know if you guys what I mean. Like you see this f from 1. Can we know that if we log the value to know what it actually is?
No, if you do the normal maths in your test, put the answer there. It will convert it, like it will bring it into the field, even if it's outside the field. It will bring it and equate it, and it will be correct. In as much as your calculation is correct. In the normal sense. Yes.
You don't the normal maths and that if you evaluate at 2.
You get something.
I'll get 5. So if I do the normal maths and I bring it into the prime field, it will give me the result.
Yeah. So even if, let's say, the prime field we're working with is mod 7, but then you evaluate that polynomial and it gives you, let's say, 78. If you do in your tests, once you do from 78 and you do like the quality check accept, it will accept. Yes.
So I was trying to of a number to get like that field stuff. Because me that now I don't know can the every operation automatically
The modulo.
modulo of that number, that prime.
Like any operation you do will give you the modulo of the number in this BN254 field. Yeah. So if you want to do like modulo, say within your code, something like that.
But this means that you no longer have to use right?
Yeah, because
you no longer have to use because automatically it's already in the field.
yes. Yeah, thank God. But let's say when you guys have gotten comfortable with all this, that's what they call like non-native arithmetic. But that one it's not something within the scope of this course. Maybe outside you can just look at it. But that's like you're working on a field, but you want to do like a modular operation within, like maybe a smaller modular operation within that big field. So now you're not doing modulo, the native modulo. You're doing modulo, the smaller modulo you want to work with. So it's kind of like, they call it like non-native arithmetic, but that's not like within the scope.
Sorry, I'm a bit confused. So this evaluation of this polynomial, with all these things we got there now, it is in what modulo? Is it just picking a random modulo to work with?
No. This BN254 has a prime. Yes, instead of 7, so I work a modulo this prime. This prime is like 256 bits representation.
It's very large.
Very large.
So they are just called small fields, right?
You can scroll up to the struct.
Like
you
Goldilocks and
define
Yeah.
there's Goldilocks, that's smaller. It's just like a U64. So fields are not necessarily always very large.
Yeah. So there's the missing 31.
Will be as secure as this like number?
No.
Yeah, it won't be as secure.
Depends on your protocol.
It depends on your protocol.
Yeah. So protocols that require a large field, I want to use a small field because small fields are more efficient, right? So if you're doing like additions and multiplication in a small field, it's a lot faster than doing it in a large field. Because a large field has so many like wasted space. Let's say you want to represent 2 and you're using a 256 bits. When 2 you can just represent it 1.
With 1,
So you have like 0,
1 and 0.
and you have to do addition and stuff, so it's good to do addition across all the bits because the computer cannot predict what you have. So arithmetic is faster in small fields, but then bigger fields are better for security because you're always sampling random numbers and you don't want to be predictable. So if you're sampling from a small set, it's more predictable, it's more possible. But if you're sampling from like a really large set, then it's hard to predict which one you're going to pick. So they mix it. So there's something called a field extension in those small fields. So you have a small field and you can extend the field to something bigger. So you do your arithmetic in the base field, that's what you call it. Then you do your sampling in the extension field. We might talk about it.
So,
Yes.
I have one question. Is the extension field the way it is in math? It's the same thing.
I think so, yeah.
Okay.
You're just increasing it. So you're able to do that.
The prime number will just be raised to power n, and then it's greater than 1.
And n is the
N is enough, yes.
So, like, does everything make sense up to this point? There wasn't really much we did, right? Yeah. We just converted to a prime. Yeah. So, but like, the whole converting process makes sense, right? And say we have to go ahead to implement Shamir with the field. We know how to go about it, right? Okay. So, for those of us that have implemented Shamir, we will now be expected to change our type to a field element, right?
Please, I just have a question. So
Yeah.
last time I kind of forgot. I think you told me before. So that time we had it outside this implementation.
In the
Can I
test.
just throw the example?
Okay, outside.
Yeah. Okay, don't worry. I should ask it.
Okay. Yeah. Okay, so a field element and another field element. Yeah, so it's just normal multiplication, right? Well, but when you do multiplication, it's possible that you get an element. It's possible that your result may be outside the field, right? So after doing the multiplication, then you mod it with the prime.
Would that be a function of equals to prime?
Huh?
Would that be a function of equals to prime? Or why do we need the prime?
Okay, no, like when you're implementing, you don't need to you don't need to think about that. He was asking a question, I think, outside.
Field.
Is it outside this?
Field times field.
Okay, based on this. No, just do your normal multiplication.
Sorry. So, in your implementation for more add and also, did you restrict or you just put the F? Do you also
You have to restrict. You have to restrict. There's it. You have to restrict. If you don't restrict, it won't even compile. So there may be situations where you want it to implement the prime field traits. Say you also want it to implement some other traits. So you just add. Maybe if you want it to implement, let's say FFT friendly. So you just keep adding them, like all the traits you want it to implement. So anything that you're now using here in your test must satisfy all those traits. I don't know if it makes sense. Okay.
Sorry. I want to ask a question.
Okay.
Based on what it asks, if we have two finite fields that they are not defined under the same
Under the same.
There are two different finite fields. That means their elements are not the same. Is it possible to multiply them? Do we have to, like, the multiplication, will it be that we will define a polynomial with the domain of that field? Two polynomials, then we now multiply, or we can just multiply them outright?
No, you can't multiply them outright because they are like from two different fields, right? So in that situation, what you do is you either bring one to the other one's field and then do the multiplication there, or you take two of them to a common field and do the multiplication there.
Okay.
The whole concept, like this Chinese remainder theory stuff. Right? Okay, so I think that will be the majority of it for today.